Welcome to the Artha Engineering motor controller demo. We have over here on the left our very first proof of concept prototype motor controller. And what this motor controller does is supply this electric motor over here with enough power to do the work that it needs to do, but no more. So as we vary the load on that motor, give it more work to do or less, we supply only enough energy so that the motor can maintain speed, but no more. And there's quite a bit of energy savings to be had in that. So what we'll do is, we'll generate electricity with this alternator, and we'll light these car headlights up to varying degrees, and we'll watch this power meter and see what our power savings is as compared to shorting this motor controller out. We'll take this out of the circuit so we can see how much power the system would use if we were just pulling it right out of the wall without the motor controller. So I'm not going to describe in depth how an alternator works. You'll have to go Google that. But in an automobile, it's hooked up to the battery, of course, and that supplies an amount of current that allows the alternator to generate electricity. And we're replacing that battery in a car with this benchtop supply. So as I turn this knob right here next to A for amperes, which is a unit of current, as I turn this up and down, we can change the amount of current to the alternator, which increases or decreases the magnetic field, which causes us to be able to generate electricity. And in this way we can repeatably and with some degree of precision change the load on the motor for comparison purposes, with and without this motor controller. So I'm going to start this demo by removing the belt. So we're going to start with the unloaded motor. We're going to control it, and then we're going to short out the controller and see what our delta is there. And then we're going to add the belt, and we're going to increase the load, and we'll just watch the power savings under different load conditions. Okay, so now I've removed the belt, and we're going to just spin the motor with no load, and we're going to monitor how much power we're using to just spin the motor in an unloaded condition with our motor controller. So I'm going to flip the switch here, start the motor up, and then you see we're at about, as the motor warms up, it'll get a little more efficient. So we're about 160 watts just to spin the motor. Now what I'm going to do with this clip lead is to short out the incoming power to the outgoing power, thereby bypassing this whole circuit. So we're going to basically short this black wire to this black wire, line to the load, and remove this from the circuit. And let's keep an eye on our power meter. See, it's drifting down already because the motor warms up. About 156 watts or so. There we go. Short the motor out. There we go. And now we're all the way up to 333 watts of power. So quite a substantial increase, about double the amount of power to spin the motor. Taking this off, and we're back down to about 155 watts. So next I'm going to put the belt on, and we're going to drive the alternator with the motor, and that'll put a substantial load on the motor, and then we'll watch our power meter and see what we get. Now we've got the belt on the pulley, so now we're going to drive the alternator with the electric motor, start this up. Remember, unloaded we were at about 155 watts, so we should see an increase. So now we're at about 200 and probably on average about 225 watts of power. So it takes more power for the motor to spin the alternator. We're still not lighting the car headlights. And so now we're supplying the motor with more power because it needs more power to do the work that it's being asked. And so once again, I'm going to short out our motor controller, and we'll keep an eye on our power meter and see how much power it would take to drive this system, which is about a 75% load. Remember that this alternator would normally be on a car which would be at least a 100 horsepower motor, and we've got a 1/3 horsepower motor. So this is a very substantial load for this little motor, and I estimated it's about 75% of its capability. So we'll short this out, keep an eye on our power meter. And then we are at about 357 watts. Dramatically more power without the motor controller. One more time, I'll take this off, and then we'll watch that power drop right down. One thing I want to point out, this motor controller, it is our very first proof of concept. This could shrink down to the size of a pack of cigarettes quite easily, and maybe even as small as a pack of gum, and use very little power itself and very cost effective. The fundamental technology here has no software, no microprocessors. There's no sensing wires, there's no external sensors or feedback circuits. There's just power going in, power going out, and nothing else. So it's really elegant, really simple, and very robust, and can be made very, very cost effectively and quite small. The next thing we're going to do, we're going to start supplying current to the alternator so we can get these headlights to light. So I'm going to turn the current on our bench supply up to 1 amp. And as I do that, you can see the power meter climb. So now we've got a little bit of glow in our headlight. We've increased our power usage. Once again, the motor controller is engaged. We're up to 270 watts on average to do this. And one more time, I'm going to short out the motor controller so that we can see the increase. There we go. Now we're at 370 watts. Yeah, about 370 watts. And now we're well in, probably about 80 to 85% load on the motor at this point. And I'm going to increase it even further. So here we are again. 1 amp, motor's being controlled, we're about 270 watts. I'm going to increase this even further. We're going to get those lights to glow a little brighter. Take it up to about 1.5 amps. Now we've got quite a substantial load on the motor. We're up at about 328 watts of power. I'm going to short out the motor controller one more time. Here we go, there we go. And now we're up to 385 watts roughly. So the differences are getting smaller and smaller because as we put a bigger load on this motor, it gets more efficient. So now we're going to take it up to a full load. We're going to make these lights glow quite brightly. And we'll go up to about 2 amps, which is now, at this point, we've got a fully loaded motor. If I turn this up much more, the motor would actually stall. We're controlling the motor, nice bright lights. It's taking just about 400 watts, 390, in the high 390s, 400 watts roughly. One more time, I'm going to short out our motor controller and see how much power it would use to do this if it were just plugged into the wall. Here we go. So here you see that a fully loaded motor is as efficient as it can get. There's nothing to be done. But that's not how motors are used. Typically, they're running below 75% of their rated load. And so there's a great deal of opportunity for a device like this to save energy on motors of all size. One thing I want to point out is that this is scalable. We're driving a 1/3 horsepower motor right now, but it could be any size. It could be a 3-phase motor. It doesn't matter. This technology is perfectly scalable and adaptable to these different conditions. So there's our demo. Thank you very much for watching.